The mole. And let's talk about that, the mole. The mole, Avogadro's number, and dimensional analysis. Oh my. So this unit's all about quantities in chemical reactions. And when we say quantities, of course, what we mean by that is... Sorry? Yeah, absolutely. But even more generally speaking, just numbers. Just numbers. We're now going to work with numbers. We've already worked with numbers a little bit in chemistry, in that you always had to balance chemical equations, right? Now we're going to go a step further, and in dealing with numbers, we're going to work with weights and masses and volumes, right? And as you keep going in chemistry, on top of that, we'll talk about concentrations and eventually temperatures and energy released and all these things, and all those things are going to be measured in numbers. So that's going to take us into a new, more complex dimension. On the other hand, it's also going to make things a bit more physical, because up till now, you've always had to balance chemical equations and think like, well, 2 atoms react with 3 atoms to make 1 molecule, and that's very hard to picture. Whereas where we're headed, you're going to be able to say, ooh, I should get this much of this thing and this much of that thing over there. Does that make sense? In weights, in a concept you can understand. So, by the end of it, you should be able to predict not just the products of a chemical reaction, but how much product should be produced. Like many things in life, this is easier said than done. Consider for a moment the simple chemical reaction of solid magnesium with oxygen, right? If I have magnesium reacting with oxygen, I should get what? Magnesium oxide, and magnesium wants to give away how many electrons? And oxygen wants to take how many? 2. And so here we are, and of course this is a perfect balanced chemical reaction that you will find no fault with, and we can move on. Yes, Autumn Appel. I'm trying to teach chemistry here. You're right, I'm sorry. There we go.
I'm not even feeding into it. You know what I'm saying.
So I'm good then?
No. If you want to think you're good, then you're good.
Oh, let me tell you, I want to think I'm good. That's very important to me, Autumn Appel. Am I good?
No. So good. No. You're the greatest historian.
The greatest. No, but of course, Autumn is correct. When we say it's diatomic, she means oxygen. So the oxygen is diatomic, which means this. When you sort it all out, this reaction tells us that you have to do what? Say this, explain what's happening down at the actual atomic level in this reaction for me. Somebody say it in words. What is this reaction? Yeah, go. 2 magnesium whats? Because like, when we say 2 magnesiums, it's like 2 rabbis walk into a bar kind of thing. 2 magnesium atoms. Okay, so we have an atom of magnesium and an atom of magnesium. Okay, keep going.
Yeah.
Which is what? Don't wave your hands at me. It's a fair question. That's a fair question. What's oxygen gas? A molecule. Good, which means it is actually also 2 oxygens, but the difference is these 2 magnesiums are kind of free of each other. These 2 oxygens are they're bonded. They're stuck to each other. Good, with a covalent bond. You're doing great, by the way. Sorry if I'm seeming negative. You're doing awesome. And what happens to them? Good. And when they react, we mean in some way or another they bump into each other. And those 2 oxygens that used to be stuck to each other, they get separated. That bond gets broken. That's going to release some energy. But then a new bond forms. And the new bond forms because these oxygens do what with these magnesiums? They react. And how do they react? What kind of compound is this? Ionic, which means what? How did they react? No. Gave away. Who gave away? Magnesium. And who took them? Oxygen. So here's what happens in the reaction. Right now, oxygen sharing, and that's a fine enough arrangement, but they bump into these magnesiums. These oxygens think, hey, sharing, that's for losers. You know what I could be doing? Stealing. And so they break that bond. They each just give each other the electron back, and they say, like, do your thing. And they bump into these magnesiums. They all take that. They take those electrons, and boom. Now the oxygens are negatively charged, the magnesiums are positively charged, and they're stuck together. Quantitatively speaking, for this to work, it takes 2 magnesium atoms to bump into 1 oxygen molecule. And when we're done with that, we get 2 formula units of magnesium oxide. Does that make sense? That's how we read that chemical equation. It's set up in the back for you, kiddo. All yours? Yeah, I put it right on the middle table for you. How about if you need anything, you know where to find me, okay? So we say that 2 magnesium atoms should react with a single oxygen molecule to produce 2 formula units of magnesium oxide. Now, if I used 4 magnesium atoms instead, how much oxygen would I need? 2 what? 2 molecules, right? So not O2, but 2 O2. What if I used 20 magnesium atoms? How much oxygen would I need? Good. What if I used 200 magnesium atoms? 100. Okay, so we get the basic relationship there. Does that make sense? This is a recipe of sorts. Now here's the problem. Okay, go back into the lab, and what I want you to do is get 2 magnesium atoms. All right, this is going to be our lab. Go back there. Put your safety equipment on, of course, because we're going to be burning magnesium here, so we've got to be safe. And put the lab coat on. Maybe we'll get gloves on. And now what I want you to do is take 2 magnesium atoms and react them with 1 oxygen molecule. Go. What do? Well, yeah, safety first. After that? They're small, right? Does that make sense? What if I told you to get 200 magnesium atoms? That's bigger. That's a lot, right? And then you'd said, if I got 200 magnesium atoms, how many oxygen molecules would I need? Okay, go do that. What's the problem? They're very small. Does that make sense? They're really, really, really small. And practically speaking, we can't work with individual atoms and individual molecules. But at the same time, that's what all our theory is based on. Everything we've taught you is one of these atoms bumps into one of those atoms, and it makes 2 of these molecules, whatever, right? Does that make sense? So the thing is, we actually physically can't do anything that our theory tells us to do. We can't count out atoms. Atoms are tiny. Just to get a sense of how small they are, this is an example of basically the smallest thing we can take a picture of accurately. This is a real photograph. Not a photograph. Photo means light. This is a real electron micrograph. You cannot take a picture of an atom with light because the waves of light are just too big. It's impossible. You can shoot a beam of electrons at it, have the beam of electrons bounce off, and measure how the electrons bounce off and make a sort of image that way. That's what an electron microscope does. And the most expensive electron microscope we have in the world, which costs about $20 million to build and requires like supercooling and all sorts of crazy things, can take this picture, which is a picture of this molecule. And I don't know if you can notice, can you make out individual atoms? I can't. I sort of see a hazy shape. Pretty cool. That shape matches exactly what our chemistry had always told us the shape should be. So that's neat, right? That we figured out on pencil and paper in 1935 what the shape of something could be. And by the 2010s, we could take a picture of it and we were right. That feels good, right? On the other hand, are we taking pictures of individual atoms here? No. And what we sure as hell couldn't do is reach down with a pair of tweezers and start moving those atoms around. Does that make sense? Just simply not possible. So, how do you work with something tiny when you're really big? Because that's the real point. It's not that atoms are tiny. Atoms are the size they are. The real issue is that we are very, very, very big. We're made up of a huge number of atoms. David Blattner, in his book called Spectrum, which is a great book, would recommend, did some sort of back-of-the-napkin calculations to figure out how many grains of sand were on the planet Earth. And the number he came up with is about 7 times 10 to the 18. And do we remember our scientific notation? That means a 7 and then multiplied by 10 18 times. In other words, 7 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's about that many grains of sand on planet Earth, give or take. It's a guess, right? Los Sandra. That's a lot of sand, right? You could spend your whole life counting that and you'd never get there. Just to give a sense, that is a million times a million times a million times a million again times 7. And that's about, that means that every person on Earth, and remember there's about 8 billion people on Earth, could all have 200 million grains of sand all to themselves. A lot of sand, right? That seems like a big number, but it pales in comparison with the number of stars in the universe. Scientists disagree pretty strongly about that number, but some of the best estimates we have put it at about 7 times 10 to the 22. That is a 7 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 zeros after it. That is about 1,000 times bigger than that. That means that every grain of sand could have 1,000 stars. And since you have 100 million grains of sand to yourself, that means that you can have 100 billion stars to yourself. That's pretty good, right? Every single living person can have 100 billion stars. Now, to give you context, and I've probably mentioned this to you if you took chemistry with me at any point, but I just think it's something silly, because what's sillier than a baby fingernail? It's just a stupid little thing, right? Just a stupid, silly little thing. And it's also made up of about 7 times 10 to the 22 atoms, one for each star in the universe. That is just a staggering number. You're really big. There are more water molecules in a single human tear than there are people who ever lived. I came up with that, and I think that's kind of profound. It's overwhelming to think about. And what it means is this. If there's more water molecules in a tear than there are people who've ever lived, then we're not going to go in the back and do chemistry with one atom at a time. It just doesn't work that way. Does that make sense? They're just too small. We're just too big. So what's a boy to do? Well, when I am struggling with something in life, I like to think about things that I feel comfortable with. And you know what makes me comfortable? Donuts. Love donuts. Big old fan. And now, if you want to, if you're a sucker, can you go buy one donut? Well, of course you can. You go to Tim Hortons, you say, I'd like a donut. But this is not what we do. How do we buy donuts? You buy them by the dozen. And then you say, I'm just going to have one. And you go, well, that was pretty good. And you say, well, maybe just 2. And then before you know it, you've eaten a dozen donuts. Anyway, enough about me. The point being, when you buy donuts, you buy them by the dozen. And if you wanted to buy enough donuts to feed 60 people, you actually don't go and say, I need 60 donuts. What you actually say is, like, could I get 5 dozen donuts? Right? That's how you order. They'll give you 5 boxes of a dozen donuts. Why do they do it that way? Why not just say 60? Can I get 60 donuts? Why 5 dozen? Doesn't that seem needlessly complicated? Yeah.
Because that's how they sell it originally. So
Sure, and why is that how they sell it?
it's easier than just having one.
And why? Because you're right, it is easier. What makes it easier?
Most people will buy the donuts for like their family, so saying like, can I get like how many donuts instead of, but then you just get a dozen.
Yeah, they don't want to have to work with, this person wants 8, that person wants 9, that person wants 4, that person wants 7, this person wants 14. They say, no, we sell, you can buy them one by one, but it's a bit more expensive. And if you want them at a reasonable price, we sell them 12 at a time. You can buy 12, or you can buy 24, or you can buy 36, you can buy 48. But you can't buy 42, not cheaply, not the way they sell them in bulk, right? It's like the classic thing about how there's a different number of hot dogs in a pack than there are hot dog buns in a pack, which admittedly is frustrating, but all the same, these things are sold in packages, right? And we do that because it lets us work with bigger numbers easier, right? That's all today's lesson is, which is we sell donuts by the dozen, and we have to sell atoms by some kind of big number too. Does that make sense? Now, it's going to be a lot bigger than a dozen. But if you understand how a dozen works, then you're going to do fine with today's lesson. The idea of a dozen is that if I say I want 3 dozen, what am I really saying? 36. If I were to buy 10 dozen, what am I really saying? Oh, you guys are good. What if I bought 1,000 dozen? 12,000. Does that feel comfortable for everyone? Like, not to be condescending, that's seriously the whole lesson. If you understand that 1,000 dozen donuts is the same thing as getting 12,000 donuts, you're good. You got this covered. You check on Jana and see if she looked stressed out. I wonder if she's having trouble finding the lab prep or something. There's a lab prep up for them for the esters lab, which theoretically we're going to run tomorrow. If I don't have my space in the back, we might run it Monday because they're doing some painting back there for the play. So this brings us to the problem we have, which is that we need to count by a big number. And the solution to this is to use a counting number called the mole. So like we said, a counting number is a unitless number that we use in place of a number for counting purposes. The most common is probably dozen. There are 12 in a dozen, so a dozen donuts means 12. 2 dozen cats would mean 24 cats. If you have 2 dozen cats, it also means you have a problem. Yes. Because cats are godless killing machines. Do you have 2 dozen cats?
At some point, I had 21.
Well, that's not 2 dozen, so you're good. No problem. But boy, you're getting there. You're edging towards having a problem. 21, that's a lot of cats.
They were all, we like bred them. So
Yeah, well, that's different. That's different. Because, yeah, that's a lot. It's a lot of cats. It's a lot of cats. I wonder, what is the tipping point at which once you have that many cats, the first night you go to bed, they will just consume you for dinner? Do you think 50? Do you think by the time you live with 50 cats, they just eat you when you go to sleep?
You could probably
I think 50.
I feel like
I'd
it'd
do
be 450.
70. Well, 70 you're definitely done for. I feel confident in that.
450. I feel like
Anyway, the point being, cats are godless killing machines. Let's get back to work. And to be clear, I love cats. They're very cute. Just, as always, you have to know, when they're nibbling your toes, it may look cute. They're just testing the waters, Tim. Just seeing how you respond and if they can get away with it. Yeah. Yeah, you bet. There's Sharpies right here. Right here for you. All right, so we're going to use a tool to do calculations here called dimensional analysis. If I taught you math in grade 9 or 10, I probably introduced you to this, but that's okay. We're going to reintroduce it fresh here one way or the other. Dimensional analysis, I didn't learn until I was in university, and it was like somebody had turned a light on in a dark room. It makes life so much easier. And the idea is this. It's just thinking in terms of ratios and working with units. So here's the idea. In dimensional analysis, instead of memorizing a formula, here's the idea. Here's what we'd say. We'll do an example, and we're going to do an example that we have just above here, where we said 2 dozen cats means that you have 24 cats. Right now, you can do that in your head, right? Nobody needs to do any math to figure out that 2 dozen cats is 24 cats. That makes it a perfect example to learn on because we can do it in our head, but then we can also show the math. Does that make sense? So what we'd say is this. If we have 2 dozen cats, and we want to be able to convert that unit to just knowing how many cats that is, what math do we do? Well, what we're really saying is this. We're saying whatever math we're going to do, the unit dozen cats is going to have to cancel, right? Because that unit has to go away, and it's going to have to be replaced by the unit just cats. Well, how do you cancel something? Well, you can subtract it, or you can get rid of anything by dividing by itself. 4 divided by 4 is just 1. 8 divided by 8 is just 1. 11 divided by 11 is just 1. And as it turns out, a dozen cats divided by a dozen cats is just 1. Which means, in dimensional analysis, whenever we're working with units, we just multiply by a fraction. And what we're going to do is we're going to divide by the unit we want to get rid of. No numbers yet. No numbers. This is a math trick. But the great thing is it's a math trick that will help you in real life all the time. So we're just going to divide by the unit we want to get rid of. In this case, I want to get rid of the unit of dozens of cats. And then on the top, we're going to multiply by the unit we do want. And in this case, the unit we do want is just cats. Now, this is a stupid example of units, but the next example we're going to do is going to be not stupid. And now, the only thing we have to do is this fraction has to be 1. Does that make sense? Because if you multiply 1, you're not actually changing anything. In other words, you have to put numbers in this fraction such that the top and the bottom mean the same thing. So what numbers could I put here to say that how many cats is the same as saying a dozen cats? Well, we could say 1 dozen cats is the same as saying 12 cats. Does that make sense? Now, for this example, again, this is way harder than just doing it in your head. Why do all this work? But when we get to examples that have difficult, ugly numbers, this process is going to be very helpful. So now, what can we do with that? Well, we can just do the math. And when we do the math with the numbers first. What is 2 times 12 divided by 1? 2 times 12 is? Divided by 1 is? 24. But we're also, in chemistry, always going to do math with the units. What is dozen cats divided by dozen cats? Well, they cancel, leaving us with cats. So here's the general form. When we want to do dimensional analysis, we write our given number with given units. Whatever that may be. 6 grams, 8 meters, 5 dozen cats, 36 hectares. Doesn't matter. Whatever it is, you write the number and the given units. And then you multiply by whatever we want here. The important thing is we put the given units on the bottom because we want to get rid of them. And when you divide anything by itself, it goes away. And on the top, we're going to put the desired unit, whatever it might be. And when we do that, the given units will cancel, leaving us with the desired units. And the only thing that we have to know is that this ratio must be true. As long as the ratio is true, the overall math will work. It doesn't even need to be neat. Can I give you the great example to me? I can never remember, for the life of me, the conversion between centimeters and inches. I can never remember it. It's some stupid number. It's like, maybe, I don't know. But you know what I do remember? I remember my ruler from when I was in elementary school. I don't know if they still have these, but the ones we got when we were in elementary school were wooden, and then they had metal strips embedded in them, and you could peel that strip out, and you could like hit your friends with them. And that's what I remember. But you know what else I remember? I remember that on one side of the ruler it had inches, and how many inches long was that ruler? The standard like elementary school ruler. 12 inches. And the other thing I remember is that on the other side it had centimeters. And how many centimeters were there? 30. So that's all I have to remember. And now, if I want to say, well, what is 11.5 centimeters in inches? It's the easiest thing in the world. You don't have to write this. But I would say there's my given, with my given units. And we multiply by a fraction. And first we deal with units. What unit do I want to get rid of? Centimeters. So I put it on the bottom, because that will cancel. And I put the unit I want on top, inches. And now I just put a number here that needs to be true. If you remember, like written does, that happens to be that 1 inch is 2 point blah, blah, blah centimeters. Awesome. Put that in. I don't remember that number. I can never remember it. But what I remember is that my 12-inch ruler was 30 centimeters long. And now that will give me the answer to 2 significant digits, which is pretty good. Does that make sense? The fact just doesn't need to be one. As long as it's true, you're good. If you happen to know your height in inches and your height in centimeters, you could use that fact for this. Does that make sense? No matter what fact you know, as long as you put a true fact in, the math will work. Dimensional analysis. It's your friend. So this will give you a new number with the desired units. We use this all the time. Now, look at me. Early on, this is going to seem like a waste of your time. You're going to think, but I can do this so much quicker in my head, or I can do this so much quicker just multiplying or just dividing. Why am I showing all this work? Look at me. Because later on, you won't be able to do it in your head. And later on, you won't be able to just figure out, I know I just divide it. I promise, all right? We're going to do things later on that are like 26 steps. You're not going to do it in your head. And you're not going to remember, oh, I multiply by this, I divide by that. So learn to do it this way now, because yes, these questions are easy. We're doing easy questions to learn the process so that when they get hard, we know the process. Does that make sense? Let me see if I have a question. Just give me 1 second. I want to see if I have a question on here. Let me give you a prime example of this. Let's say we wanted to know how many seconds old I am. Remember yesterday, we put my age up there and we looked at like years, days, all this. What if I would know how many seconds old I am? Is that a hard question? Well, it's actually completely trivial. Look here, we can just do this. So watch, what I can say is, I know that I am 41 years old, right? In fact, we're past 6 months, so really, even though I'm 41, I round to 42, right? 41.7 I'm probably at. So I'm 42 years old. Oh my God, look at me. So there we go. Now, we can just do this. What unit don't I want to talk about? Years, I'd put on the bottom. Now, if I knew how many seconds were in a year, I could just write that here, but I don't. So you can just do it in stages. I don't know how many seconds are in a year, but I know how many days are in a year. How many? 365.25, right? Every fourth year is a leap year, so 365.25. Okay, now what units cancel? If I stopped calculating now, I'd know how many days old I am. But I don't want days. What do I want? Seconds. So I can just keep going. What unit do I want to cancel now? Days. Where do I put it? On the bottom. Now, if I knew how many seconds are in a day, I could just do that, but I don't. But what do I know about days? I know how many hours are in a day. How many hours are in a day? 24. What cancels now? Days. If I stopped calculating now, what would I know? How many hours old I am. But that's not what I want to know. So I can do it again. What unit am I going to cancel? Hours. Where do I put it? The bottom. What unit do I want? Well, seconds. Do you know how many seconds are in an hour? I do because I teach physics, but you probably don't. Probably you do know, though, how many minutes are in an hour. So let's go with that. How many minutes are in an hour? Okay. What units cancel now? Hours. What would I know if I did this calculation? How many minutes old I am. But that's not the question. The question is how many seconds. So what do I do again? Fraction. What unit do I want to cancel? Minutes. What unit do I want instead? Seconds. How many seconds are in a minute? 60. What units cancel? When I do this math, what will I know? How many seconds old I am. Does that make sense? And now we can just do it. We can say, okay, let's do that. 42 times 365.25 divided by 1 times 24 divided by 1 times 60 divided by 1 times 60 divided by 1. Yeah. That's a good question. No, but even still, I want to build the habit of doing it because it won't always be ones on the bottom. So I just want to build that habit. Multiply by the top, divide by the bottom. Mathematically, are those ones doing anything? But thinking-wise, they're actually important. So my advice is do it. Now, again, mathematically, it makes no difference. But if you build the habit of multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, you won't screw it up later. So my advice, put them in. But I'm dumb. Like if you can handle that, awesome. I just need to do it the same every time. And what we end up with is that I am 1,325,419,200 seconds old. That's a lot of seconds. By the way, how many sig figs do I have? And that's interesting because all of these, 60 seconds in 1 minute, that's infinite, right? That's a definitional thing, right? The definition of a minute, 60 seconds. So there's no count, that's just counted, right? Same with 60 minutes being 1 hour, that's just counted, right? Same with 24 hours being 1 day. All of those things are just the definition of those things, right? Likewise, 365 days being 1 year, that is definitional too, right? And the reason I'm able to put 0.25, even though it's counting, is because what we really know is that it's 365 plus 365 plus 365 plus 366 is 4 days, right? Does that make sense? So the only measured number here is my age. And how many sig figs in my age? Only 2. So I have to round this answer to 2 sig figs. So I can say that I'm 1,300,000,000 seconds old. Or if I want to, I could say 1.3 times 10 to the exponent 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Does that make sense as a process? See, like that's a question that if you did it traditionally, you'd be doing a bunch of little tiny calculations and then saying, okay, now I'm going to use this number and do it here. Oh, now I'm going to use that number and do this with it. Okay, now, whereas here, one big math equation. And do you see how you can just talk your way through it? I'm 42 years old. Oh, but I know there's 365.25 days in a year, so I can figure out how many days old I am. But then I know there's 24 hours in a day, so I can figure out how many hours old I am. But then I know there's 60 minutes in an hour, so I can figure out how many minutes old I am. And I know there's 60 seconds in a minute, so I can figure out how many seconds old I am. Do you see that? It's just this very logical flow. That's the power of dimensional analysis. So let's try one here. We'll do one together, and then we'll do one here. How many people are in a crowd of 32.5 dozen people? So if for some reason you read a newspaper report and it said it was a crowd of 32.5 dozen people, first you'd probably think, why are they talking this way? But having said that, what do we do math-wise? What do I start with? I start with my given number with its given units. So I'd say 32.5 dozen. And then we always multiply by a fraction. You do that without even, I don't want you to think about it, just put your given, multiply by a fraction. And now numbers come second. We deal with the units. What unit don't I want to talk about? Dozen. Where am I going to put that? On the bottom. What unit do I want to talk about? People. Okay. And now we can put the numbers in. And the nice thing is, if you say it out loud, you'll know if you've screwed it up. Watch. What does that say? Say it out loud. That says 1 people is 12 dozen. Is that correct? Do you see how you almost can't get it wrong? As long as you say it out loud, if I try to do the thing where I do it wrong on purpose, which, spoiler alert, I'm going to do it so many times, but you're going to know, because all you have to do is say it out loud. We know that 12 people is the same as 1 dozen. And what units will cancel? Dozen will cancel with dozen. And here we go. 32.5 times 10 would be 325. And then 325 on top of that would be 65 for a total of 0. Okay, 1, 6, 2 is 8. So 390? Is that 390? All right. And there we go. 390 people. So in a crowd of 32.5 dozen, there are 390 people. How's that feel? Does it kind of make sense? That process. I don't care that you know how many people are in 32.5 dozen, but I do care that this process start to make sense. And at first, it's going to feel clumsy. It's going to feel like a waste of your time. Look at me. It's not a waste of your time. It feels like a waste of your time because right now we're dealing with trivial, stupid little questions. And you're like, I could just multiply that by 12, idiot. But trust me when I tell you that we're going to get to stuff where you aren't going to just know, well, I just multiply it. All right? You got to trust the system. Yeah. Sure, if you want to. Absolutely. Ready? If I had 945 people in a crowd, how many dozen is that? It's trivial. You'd say I have 945 people. You don't have to write this because there's no question asking it. And we'd say, okay, I don't want to talk about what? Where would I put that? Okay, what do I want to talk about? Okay, and then now I need to put numbers in here that are true. How many dozen is a people, or how many people is a dozen? Yeah, 1 dozen is 12 people. Now again, you may be like, hey, dummy, I could have just divided by 12. Yeah, of course. But again, understanding the process is good because what unit cancels? People. And that means mathematically this has to be true. By the way, what is that? How much? 70? Like that? Awesome. Does that make sense? So, yeah, whatever. If you want to write it, write it. So the other way around. You are going to do this, and once you get good at this, you're going to use it all the time. I use it when I'm baking. I use it when I am building things, like doing carpentry. I use dimensional analysis, oh my God, endlessly. Just endlessly. It's the most useful tool I ever learned in school. You use it for everything. Because it's just a way of dealing with ratios, but it's a really logical way of dealing with ratios. Change your life. Change your effing life. All right, so Gettysburg Address. Who gave it? One of the most famous speeches of all time. Does anyone know? The Gettysburg Address. Who delivered the Gettysburg Address? It was delivered at the Gettysburg Battlefield, which is a Civil War battlefield, where tens of thousands of people died in a single day of battle that was famously vicious during the Civil War. And it was a year later. It was commemorating the spot. Before this person got up and spoke, a preacher got up and spoke for 4.5 hours. Apparently it was riveting and the crowd was really into it. This guy got up and spoke for like 3 minutes. And it's a famous speech, one well-known name. It's by Abraham Lincoln. And it starts with a rather florid thing where he says, 77 years ago, our forefathers, blah, blah, and he gets going. But 77 years ago, what the hell does that mean? Anyone? 80. Might help if you speak French, by the way, because they still talk this way. We don't anymore. We've gotten less fancy in our times, but the French still do exactly this. Might it help you to know that a score is another way of saying 20? So 77 years ago is like saying 420. Nice. Years and 7 years ago. Again, what does that mean? Right? It means 80. Does that make sense? Like en français, 80, right? They still say it. That's still how they talk. If they want to say 80, they still say 80. We used to do the same thing in English. 80. Now we say 80. I always maintained that they should say like wheaty, nifty, sancty. Wouldn't that be better in French? If it was like sancty sank instead of... Anyway. Right? I think that'd be better. Wheaty wheat. Wouldn't that be better? Anyway, point being, 77 is 87 years ago. Lincoln is saying 87 years ago we founded a country. But he's saying it very fancily. 77 years ago, our forefathers brought forth upon this. I had to memorize that when I was in school. You guys didn't have to memorize that. You didn't even read it. Gettysburg Address, famous piece of oratory. Do you guys still have to give speeches every year in elementary school? Oh yeah, when I was in elementary school, every year you had to write and then deliver a speech in front of your class. And then sometimes they'd be like, that was good. Now you have to do it in front of the whole school. I remember once I had to give a speech in front of the whole school about my dog. And I hate public speaking. I still hate public speaking. And I cried about it for days and begged my mom to let me stay home from school. She did not. Anyway, that's the end of my story. Point being, though in fairness, I think she did let me stay home from school the day I was supposed to do it in my class because I hadn't written it yet. So really, I was begging to get out of school twice, and that wasn't going to happen. Jane wasn't the type to let you out of school once. So if we didn't know that 4 score meant 80, we could figure it out. Because we could say 4 score, and then what do? We multiply by a fraction. No numbers yet. And before we do numbers, what do we deal with? Units. And we don't want to deal with score, so we put that where? And instead, we just want to deal with years. Not score years. I guess I should have put years here as well. And we said here that a score is how much? So 20 years is 1 score. And now, sorry? Yeah, score years. Sorry, you can't tell because that's the messiest thing a human being has ever written. Oh, stop being a baby, honestly.
You could just redo your whole lesson at this point, actually. If you look at, honestly, it does and above, the Z looks a little weird, maybe change that.
Why is the phone?
Okay, let's get back to work. So, what units cancel here? Yeah, score years cancels. What unit remains? Just years. And then the math is trivial. What is 4 times 20? Divide by 1 is? Still 80. Good. So that's saying 80 years, which means 4 score and 7 more would be 87 years ago. Okay. Why are we doing all this? Well, the answer is we're doing all this because when I want donuts, I don't want a donut. I want a dozen donuts. And when we go in the back to do chemistry, you cannot count out an atom. You can't do it. So we picked a nice big number that, as it turns out, you can count out. And we'll get to how you count it out tomorrow. All right? Tomorrow you're going to trust me. Today, I'm just going to tell you what the big number is. And we picked a nice, easy to work with, very round number. And we call it the mole. It's very simple. We say that 1 mole is the same as 602, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, so it's a perfectly logical number that's easy to work with. 1 mole is the same as that many things. So a mole of things is that many things. Now, do we want to write it that way? That's begging to have a mistake. So we're going to write it this way. We're going to say 1 mole of stuff, 1 mole of something, is the same as 6.02 times 10 to the 23rd things. So if we're talking about a mole of donuts, that would be 6.02 times 10 to the 23rd donuts, which could not possibly exist. But if it did, I would do my God's honest job to eat them all. But
I think you would die.
I would die of old age, if nothing else, right? Like,
Your amount of sugar, though. I think
yes, yeah. I mean, there's multiple problems. We can all agree I'm unlikely to eat a mole of donuts. But listen, I'm not a quitter.
Are you allowed to take?
Okay, shh. You're allowed to focus on my lesson. Okay, so now, listen. We will get to why this specific number tomorrow. For now, you just have to trust me that it actually makes a lot of sense. In fact, it's a great number to choose. It's really logical. For today, you're just going to have to trust me that there's a good reason not to choose a nice round number, right? Like, you'd think that 1 times 10 to the 23 would be easier to work with, right? But for reasons we'll get to tomorrow, you have to trust me that this number is the logical number. And the nice thing is, after today's lesson, we won't work with this number directly ever again, because we're never going to count out atoms again. Am I ever going to ask you to go in the back and count out 6.02 times 10 to the 23rd atoms?
Yes.
No, that would be impossible, right? Like literally. There's not enough time in the history of the universe to do so. So we're not going to do that. But this is called Avogadro's number. It's named after a guy who worked in early atomic theory named, wait for it, Avogadro. And it helps us work with atoms. So for today, we're going to just look at this as an idea. So if we have 4.3 moles of carbon atoms, how many carbon atoms do we have? Because this is something we will work with in the lab. We will say, okay, I need you to get 4.3 moles of carbon. And you'll go in the back and do it. And again, tomorrow we'll learn how you do that, but it comes down to mass. We will do it by weight. But in the meantime, 4.3 moles of carbon, how many atoms are we talking about then? Well, let's do one together. If I told you to go in the back and get 4.3 moles of carbon, now, mole, that's a big word. So we need a short form for that unit. Like grams, we don't write grams, we put G because that's much quicker. And milliliters, we don't put milliliters, we write ml. So this obviously needs to be shortened. So we have a very convenient short form, and it is MOL. That's right.
Oh?
Yeah. That, my friends, is 33% shorter. So that's pretty efficient, right?
Wouldn't it be 25%, not 33?
Well, it depends on how you want to think about it, because if it would certainly be 33% longer if we wrote the E, right? Right?
Okay.
Yeah. So you're right. I suppose we have reduced it by 25, but it's an efficiency of 33% that we would lose if we went the other way. Percentages are weird, right?
Yeah.
The one thing you learn in business, that the way you pick your percentages makes things sound really different. So you pick the one that sounds more impressive for the thing you're currently trying to do. You're talking about a loss, you find the way to make that sound as little as possible. You're talking about profit, you want to pick the way that it sounds big. Anyway, it's a different discussion. Okay, so if I have 4.3 moles of carbon, we're just going to do some dimensional analysis. When we do dimensional analysis, we multiply, we don't think about it. We multiply and we draw a fraction line. You are never going to think about that, you're just going to do it. You write your given, you multiply, you draw a fraction line. No thinking. Next, no numbers. What do we deal with? Units. What unit do I not want to talk about here? Moles. Right? So there we go. Now, something else. We're going to develop this habit of putting a subscript on our units so we know what we're talking about. This isn't just random moles. This is moles of carbon. So I don't want to talk about moles of carbon. I want to talk about carbon atoms, right? Does that make sense? You don't have to do the subscript thing. It doesn't change the math. But when we get to a question where we're dealing with 6 different chemicals, is it going to make sense to label which one's which? A lot of sense. Does that make sense? And we do that by putting subscripts after the unit. Now, we need to put a number here that's true. And what is true is that the definition is that 1 mole of anything, hello, today's note is on my lectern. Thank you very much. 1 mole of anything is how many of those things? 6.02 times 10 to the exponent 23. Now, your calculator has a scientific notation button. Every calculator is different. Some show it this way, but you gotta watch out. Look at me. This is so important. Look at me. You have to watch out because most don't. Because there's also a logarithm button that looks kind of like that. Most calculators show it, and this is so stupid, with that. Or even more annoyingly, I have no idea what it means, with that. If you're not sure how to do it on your calculator, come ask me. I will show you. You do not want to be typing this in as 6.02 multiplication button, number 10, exponent 23. Not how you want to be doing it. Your calculator has a button that means times 10 to the exponent of question mark, and all you have to do is press this, then 23. Does that make sense? Every calculator is different, so if you're not sure, ask me. Sometimes it'll even be a single E. That's really stupid. I hate all of these. I wish it said scientific notation. That'd be better. Like, why couldn't it say psi naught? Why not, is my question. Something like that. I don't know. But anyway, you have to know how your calculator does it. On this stupid computer, you use a capital E. I hate that, but that's what it is. 4.3 times 6.02. That E means times 10 to the exponent of. So what's the only thing I have to put after that? 23. You must figure out on your calculator how to do it. I promise you will drive yourself crazy. It will work if you do it by multiplying by 10 to the exponent of manually, but you'll drive yourself crazy. Your calculator work will be much messier, and it just gives you way more digit pushes to make a mistake on. Figure out how your calculator handles scientific notation and know it well. And then, what do I have to divide by here? 1. And when I do that, it's going to do a bunch of math, and it's going to tell me that the answer is 2.59 E24. What's that E mean here? Times 10, not to the exponent. This isn't 2.59 to the exponent 24. It's 2.59 times 10 to the exponent 24. Does that make sense? Everybody's calculator is different. You have to know how yours works. So what's the answer here? What am I writing here? Oh, good. How many significant digits do we have here? 2 significant digits. How many significant digits do we have here? 3 significant digits. This is a counting number, so it is infinitely significant. So which one of these is the least significant? Yeah, our least precise number is that 2 sig figs, so this has to be rounded to 2. And is this closer to 2.5 or 2.6? Yeah, way closer, right? It's 2.59. So the answer would be 2.6 times 10 to the exponent 24. Now look at me. If you ever give me an answer on a piece of paper, look at me, that says 2.6 E24, I will go let your dog out and hope it runs away. And I mean it. All right? This is how your calculator may spit it out at you. We are smarter than our calculators. All right? I want things in I wish some newer calculators actually just show it in scientific notation. Much better. That's how it should do. But if you have an older calculator like this, or not that this is older, or just one that handles it by using E for scientific notation, you have to know what that means. And what it means is times 10 to the exponent of what? Oh, in this case, 24. Does that feel okay? Okay. Yeah.
Would you be able to show me?
Yeah. Shut up. Yeah, so yours is nice actually, and it gets its own button right there. So that's beautiful. What make is this, Casio? I gotta say, Casio going up in my estimation. It's right next, down at the bottom, important number, and it just says times 10 up with the X. That's a good button. I wish they all looked like that. Yeah, so try that. That should be good for you. All right, any questions about that? On your calculator right now, do this math. Make sure you get that answer. All right?
Ooh, and it shows up the total times 10 to the
Let's see.
power.
Oh, yeah. That's good. That's solid. Good calculator. Way to go, Casio. I wonder, we just bought all these new Sharps. I wonder how they handle it. Let's find out.
Oh, they have the second page.
Oh, it's EXP. See, I like that a lot less. Right? That's worse, right? But it does work. But I gotta say, advantage Casio on this one. Advantage Casio. That's better. 4.3 times 6.02 times 10 to the exponent of 23 divided by 1. Okay, now, can I tell you this? Look at me. The reason we like this is when you use the scientific notation button, your calculator works with that as a single number. Does that make sense? It doesn't work with it as a number multiplied by another number to exponent. It treats it like a single number, and for all kinds of reasons, that's hugely advantageous. Okay. I want you to try the next one. How many moles do you have if you have 4.55 times 10 to the 24 atoms of something? Raw.
Where's the one on this one?
On this one, it is that double E there. So you have to go second function
Oh
there.
my goodness.
Right? So you'd go 6.02 times 10 to the 24.
You're like trying to take credit for Angela giving us
Right? So if you wanted to do, in this case here, 4.3 times 6.02 times 10 to the 24 divided by 1, it would look like that. And that's the answer we get. Does that make sense?
Yeah.
Cool. No problem. I'll be right back. Can you keep an eye on them? All right.
What?
Maybe you can do whatever you want.
Can you leave me alone, please?
All right. What do we get? What do we get? 7.56. And is that the right number of sig figs? Looks like it. With our current Avogadro's number, you can't go beyond 3 sig figs, right? You can look up Avogadro's number to more digits if you wanted, though we're never going to care. I can't stress enough, the whole point of working with this number is to not work with this number, as weird as that sounds. So today we're going to be doing counting atoms. And then you know what we're never going to do again? Count atoms. That's going to be the trick. Tomorrow we learn the trick. Today, we're in the doldrums. So how do I set this math up? What do I write? 4.55 times 10 to the exponent 24 atoms. And then we're doing dimensional analysis. So what do I do immediately? No thinking. We multiply and we draw. Yeah, we draw a little fraction line. No thinking. That's my specialty. Excellent. Slam Brady, we're going to get along just fine. Then, what don't we deal with next? What don't we deal with? We do deal with units. We don't deal with numbers yet, right? And I know this seems like, but just trust me, trust the system. I have a system. I've been teaching this a long time now. I'm an old man. Literally been teaching this as long as you've been alive. Do I find that depressing? Yes. Is it true? Yes. So, where do we put, what unit are we trying to get rid of? And where do we put it? On the bottom. What unit do we want to use instead in this case? Moles, right? So we put that on the top. Already we know that atoms will cancel with atoms and it'll leave us with moles, but this number needs to be true. And again, what I like about this is if you screw it up, just say it out loud. Watch this. Don't write this. Look at me. 6.02 times 10 to the 23rd, 1. Now that's incorrect. How do we know it's incorrect? Say it out loud. 6.02 times 10 to the 23rd moles of something is 1 atom. That doesn't make sense, right? If you say these things out loud and you have a passing understanding of what you're talking about, it will sound wrong. You'll be like, oh, that doesn't sound right. You can try again. 1 mole of atoms is a whole bunch of them. Specifically, it's 6.02 times 10 to the 23rd atoms. Is that true? Yeah, that works. Does that make sense? And then this, 4 divided by 6, that's like 45 divided by 6. 45 divided by 6, well, 6 times 7 is 42. We need 3 more than that. So this is going to be like 7.5-ish. 7.56? Great. And no scientific notation needed, right? Because 24 divided by 23. So there we go. So that's going to be 7.56.
Times 10 to the power.
Shouldn't be times 10 to the power of anything. I mean, it should be times 10 to the power of 0 if you want. And if you've got a times 10 to the power of left over, you're not getting your calculator right. Was it 7.56?
Yeah.
Okay. And then what's the unit? Moles. Now again, if you are doing scientific notation by typing in times 10 to the exponent of, you will get the wrong answer because it's only going to divide by the 6.02. Then it's going to multiply by 10 to the 23, and you're going to end up with 7.56 times 10 to the exponent 46, which is not what you want. Does that make sense? So you got to be using that number correctly. You will regret it if you don't figure it out. So here I would say 4.55 times 10 to the 24 times 1 divided by 6.02 times 10 to the 23 equals 7.5581. Okay, listen up. There's a couple more questions on here. I want you to try them. All right? Your homework is the questions below. Get them done. And there's a couple of minorly sneaky ones in there. Minorly. But you're smart. You're smart people. But listen, look at me. Look at me. Look at me. The math in this unit, it's multiplying and dividing and a bit of adding. That's it. That's all the math you're going to be doing. But the tricky part isn't the math. You can all multiply. You can all divide. You can all add. You can all subtract. And you have a calculator. You don't have to do this in your head. You got a calculator. But knowing what to do takes practice. And again, if I could do some magical dance up here and wave my little jazz fingers and go, ah, we all know how to do this, I would do it. Oh my God, would I do it? I'd have the highest performing class in the land. But 16 years in, still haven't figured out the magic dance. What I have figured out is that the people who practice get good at it. And the people who don't. So, what should you do? Practice. How do you get to Carnegie Hall? Practice, practice, practice. You know what Carnegie Hall is? Carnegie Hall is like, in New York City, it's like the most prestigious music hall. So like if you're like, only like the most prestigious entertainers play there. Some jokes if you ask them, you ask a guy on the street, how do you get to Carnegie Hall? The answer is practice, 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 right? What's the equivalent? Massey Hall? Anyone been to a show at Massey Hall in Toronto? Beautiful old theater. It's actually an annoying theater because there's all these columns holding it up because it's old architecture, so there's a bunch of seats where you can't see the stage. But having said that, it's a beautiful old theater. Love Massey Hall. You should definitely go see a show there. Yeah, if you're getting a good deal, it says on the website, like when you buy a ticket, it says like obstructed view. They're not kidding. It's an obstructed view. It's still a beautiful place. And again, that's where like the